This is going to cover 6.1, which is exponential functions. This material corresponds to the free OpenStax College Algebra textbook, and the link can be found within the video. So in 6.1, we're getting an introduction to what an exponential function is. We've talked about functions before. We've done linear functions and other types of functions. So in this table, one of these functions are linear and the other is exponential. The way you can tell them apart is a linear growth is the range is increasing by the same amount each time, adding or subtracting. So increasing or decreasing, really. Exponential growth is the range is increasing by the same percentage each time, increasing or decreasing, and that means you're multiplying and dividing by the same thing each time. So if you look at these, you might be able to tell that the g of x is actually linear and the f of x is the one that's exponential. You can see that the x value, the domain value, increases by 1 each time. And for every increase of 1 in the domain, the range for f, if you tried to do increasing by 1, well, you would see that that's not the same pattern all the way down. So that does not work. You can't add the same thing all the way down. That means it's not linear. What you can do, though, is if you notice that 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, you'll see the pattern is you're multiplying by 2 each time. This makes it an exponential function. Whereas in g, going from one range value or one y value to the next, you can see that in fact here you're adding 2 each time. So that makes it a linear function. So that's how you're going to be able to tell those apart. Under the exponential growth, you'll see that you have exponential growth or exponential decay. Growth means you have an increase. Decay means you have a decrease. And you'll see those as we go through some of the problems in this chapter. Okay, so some examples. Identify whether the statement represents an exponential or linear function. So again, remember an exponential function is increasing by a percentage each time, or it's a multiplicative increase or decrease. Linear is adding or subtracting the same thing each time. So number 1, the average annual population increase of a pack of wolves is 25. So it's increasing 25 each year. That's adding 25 each year. So that means that that one would be linear. Number 2, the value of a coin collection has increased by 3.25% annually over the last 20 years. This is a percentage increase. So you're not adding the same amount each time. You're adding a percentage. That means you're multiplying by an amount each time. So this is exponential. So if it's increasing by a percentage each year, that's always exponential. Number 3, a population of bacteria decreases by a factor of 1/8 every 24 hours. So this is decreasing, but it's not by a set amount each time. It's by 1/8. So it's not like you're subtracting, 2 bacteria. You're subtracting 1/8 of the population of the bacteria. So that would be exponential. Really, the key word here is a factor of. That's an exponential. Okay. So you should be able to identify them like we did in the first 3, given a statement. Here is a graph, and here are some characteristics of the graph. Let me decrease this a little bit so we can see it together. Okay, so here's our graph. You can see some points on the graph. So the blue is an exponential graph, and it's f of x equals 2 to the x. So when you have base 2 for your exponential, this is what your graph looks like with these points. Now this is the general shape of any function I'm going to put a b here, of any base raised to the x power. So as long as it's greater than 1. So like 2 to the x, 3 to the x, 4 to the x, etc. We'll have this basic shape where it's increasing over time. As you go to the left, it's getting closer and closer to the horizontal asymptote, which is y equals 0. The domain is always negative infinity to infinity because it goes forever to the left and forever to the right. The range here is always 0 to infinity on one of these basic ones that haven't been shifted. That's the range. So it's always from the asymptote up, or some cases it's been flipped. So let's see, we said it's increasing. We have the horizontal asymptote. Oh, and the y-intercept is 0, 1. So that is some of the important information you should know when you're talking about an exponential graph. All of these bullet points listed here. So an exponential function for any real number x, an exponential function is going to take the form f of x equals a b to the x, where a is a non-zero real number. That's called the initial value. So make sure you pay attention to that. They ask that in the homework about initial values. So when it's in this form, a is the initial value, and b is any positive real number such that b is not equal to 1. If b is equal to 1, then it's not an exponential function because 1 to any power is always 1. But b is a positive real number. So it's not 0, it's not negative, and it's not 1. But any other positive real number is okay for b. More bullet points below here. The range is all positive real numbers if a is greater than 0. So if a is positive, your range is all positive real numbers. If a is negative, then the range of f is all negative real numbers. Okay, so basically if your initial value is positive, you're going to be above the x-axis. If your initial value is negative, it's going to flip it, and you're going to be below the x-axis. And then you have the y-intercept is 0, a. So your y-intercept, the y value always matches your initial value. And you have the horizontal asymptote, y equals 0. Okay, so keep that information in mind. If you need to refer to it as you work through some of these in the chapter, you can, but make sure you memorize this information in the long run because you'll kind of need to know it when you're graphing or you're doing some of the things you'll be asked to do in the future sections. And on the test, you won't have this written down, so you need to kind of memorize it. Okay, so for the following exercises, consider this scenario. For each year t, the population of a forest of trees is represented by the function a of t. In a neighboring forest, the population of the same type of tree is represented by the function b of t. Round any answer to the nearest whole number if necessary. So we're going to answer these first 3 questions about that one. Which forest population is growing at a faster rate? So the growth rate is the one in parentheses. That's how fast it's growing. So the one with the larger number in the parentheses is going to be the one that's growing at a faster rate. And so I think we can agree that forest B is growing at a faster rate because 1.029 is larger than 1.025. Number 2, which forest had a greater number of trees initially, and by how many? So the initial value, remember, is the value that's in the front. So the initial value in A is 115, and the initial value of B is 82. So we would say that A has a larger number of trees initially. For the how many part, you just need to subtract 115 minus 82, and that gives you 33. Number 3, assuming the population growth models continue to represent the growth of the forests, which forest will have a greater number of trees after 20 years? by how many. So we want to find, after 20 years, how many trees are in each forest. So for A of t, we want to know A of 20. So after 20 years in forest A, we will find the population of trees by simply plugging in 20. And for that, you want to put that in your calculator. When I put that in my calculator, and it says round to the nearest whole number, so I'll say 188 because it was 188.4, so we would keep it at 188. And then in forest B, we want to substitute in 20 there as well for the years. So that would be 82, 1.029 to the 20th. And when I put that in my calculator, let's see, I get 145. Okay, and so after 20 years, forest A will have the most trees. And then it says by how many, so we just subtract 188 minus 145, and we get 43 more. Okay. So next we have directions on how to write an exponential model given 2 points. So this will be an important skill that you want to make sure you know how to do. And the examples we'll show are number 1 and 2 following. So first, if one of the data points has the form 0a, then a is the initial value. Using a, substitute the second point into the equation and solve for b. So I'm just going to stop right there because our first example matches that. So you can see that this first point is 0a. That's the initial value. Remember that an exponential function takes this form. And so they're saying that a is 6. Okay, so if you plug in 6 for a, you have that. And then you can use the second point as your x and y and solve for b. So y is 750 is equal to 6 times b to the third. And so now you just want to solve for b. So divide by 6. So 750 divided by 6 is 125. So 125 is equal to b cubed. Then you just need to take the cube root. So we need to undo that cube. So cube root both sides. And we get b is equal to 5. So now we have an a and a b. When you're writing a formula for an exponential function, you want to have a and b as numbers, and the y and the x are the variables. So you'll have y is equal to 6 times 5 to the x. So you have a number plugged in for the a and a number plugged in for the b. That is your formula. Okay, case 2 was if neither of the data points have the form 0a, then you're going to substitute both points into 2 equations and then solve the resulting system of 2 equations. Okay, so let's look at how to do that one. This is the more difficult one. So we have 2 points. Since neither of them are a, because the x value is not 0 on either one, you're going to have to plug in each x and y into separate equations. So we'll have y equals a times b to the x. So that will be 1 is equal to a times b to the third. Okay, so now what we want to do is try to solve for, let's solve for a. So I want to get one of the variables by itself. If I solve for a, I divide by b cubed. So that'll give me a is equal to 1 over b cubed. Okay? Now I'm going to look at the second point. So this is from the first point. Notice that I solved for a. Okay? So keep that in mind. On the second point, I start with y equals a times b to the x. I'm going to plug in y and x. So y is 4, a times b to the x is 5. Okay, I know what a is in terms of b from the first point. So I'm going to plug that in for a. So that will give me 4 is equal to 1 over b cubed from the a times b to the 5th. And then I can simplify that. That means 4 is equal to, that would leave b squared. And now I can solve for b. So I take the square root of both sides, put plus or minus. So b is equal to plus or minus 2. Okay, we need to go back and look at something. I want to point something out. Okay, look what I have highlighted right here in blue. B is any positive real number. Positive. So B cannot be negative. So let's go back to where we were. So if B cannot be negative, that means we can't have this part. So B is just 2. So keep in mind that B has to be a positive real number. Once you know what B is, you can take that and plug it in over here and find out what A is. So A is equal to 1 over B, which is 2, cubed. Well, that's going to be 1 over 8. So now we know what A is and we know what B is, so we can finally write our function. So y equals A times B to the x. So this one was a lot more in depth than the first one. This is more work, but that's how you need to do this one. We also want to talk about the compound interest formula. The compound interest formula is a special case. It's dealing with money. So here are what the values mean, the variables. So A of t is the account value. That's the account value at the end of whatever period you're looking at. T is measured in years. P is the starting amount of the account. So sometimes it's called the principal, the present value, but it's the original amount that you put in the account. R is the percent, the rate that you earn. When you put it in your formula, you need to make sure you put it in as a decimal and not the percentage. And then N is the number of compounding periods in 1 year. Some common ones are semi-annually, which means twice a year, so N would be 2. Quarterly would be 4. Annually would be 1. So here's an example. The value of an investment account is represented by the equation. Okay, so first they want to know what was the initial investment. So this is just a matter of knowing the formula and what the numbers mean. So the initial investment is P. It's the number outside or out front of the parentheses. So the initial investment would be $10,250. What's the annual percentage rate? Again, it's knowing where that's located. The rate is the numerator of the fraction. So here's the rate. 0.04. That is as a decimal. Remember, if you have a decimal and you want to change it to a percent, you move the decimal over twice to the right. So this would be 4%. And C, how much will the account be worth after 10 years? So 10 years, that is T. That means we need to plug that in for the T in the formula. So we'll have 10,250 times 1 plus 0.04 over 12 times, or raised to the 12 times 10. Okay, so you need to make sure you're comfortable putting this information in the calculator that's approved for the final exam. So there's no point in practicing this on a graphing calculator because you can't use a graphing calculator. So make sure that you practice this on just a scientific calculator. If you don't know how to do this on your scientific calculator, let me know, and we can work through it together. So after 10 years, we're going to have $15,281.03. It doesn't tell you what to round to, but when you're using money, you should always round to the nearest cent. And that would be the answer for part C. Next, we have the continuous growth and decay formula. So for all real numbers t and all positive numbers a and r, continuous growth or decay is represented by the formula given. A is the initial value, so you should be kind of catching on to a trend here. This number in front of the parentheses, or the number in front of the E, or the number in front, is the initial or starting value. R is the continuous growth rate, so R is the percentage growth. T is the elapsed time. If R is greater than 0, so if this rate is positive, it's going to be a growth. If the rate is negative, it's going to be a decay. For business applications, you will see this similar formula, except instead of the A, they'll have the capital P for the principal, but it's the same formula, so it means the same thing. So here's an example. A person invested $1,000 in an account, earning a nominal 10% per year, compounded continuously. So here's the difference. When we were doing compounding in the previous example, it was compounded semi-annually or annually. This one is compounded continuously. When you see compounded continuously, that's when you know that you need to use this formula instead of the other formula. So the other formula is only used if you're compounding in any way other than continuously. So we're going to start with the formula A equals P E to the RT. A person invested $1,000, so that was the initial investment. 10% per year, so 10% as a decimal would be 0.1. And then T, we don't know. Oh, yes, we do. It says how much will be in the account after 2 years. So we do know T. 2 is T. Then we're just going to plug that in the calculator and see what we get. So when I did that, I got $1,221.40. So the next two examples we have, we're going to be given charts. We want to decide if the table is representing a linear or exponential function, or neither of those. If it appears to be exponential or linear, we want to find a function that passes through the points. Okay, so the key here is looking at how the x value increases or decreases, and then how that compares to the y value. So you can see for the x, each time we're increasing by 1. On the y, I always look to see if it's adding or subtracting the same thing each time. So for 70 to 40, I'm subtracting 30. If I subtract 30 again, I would get to 10. And if I subtract 30 again, I would get to negative 20. So since I'm subtracting the same value each time, this would be linear. So for every 1 increase in x, we decrease 30 in y. So that is a linear function. To find the linear function for this, first we need to find a slope. So you need to remember the slope formula. So it's the difference in y over the difference in x's. Just pick 2. It doesn't matter which 2 you choose. So I'm going to pick 1 and 70 and 2 and 40. So this would be 70 minus 40 over 1 minus 2. So that would be 30 over negative 1, which is negative 30. Okay, so here is our slope. Now we're going to use one of the points. Doesn't matter which one. So again, I'm going to choose the 1 and 70. And you need to use the point-slope form of the equation to write your linear equation. So y minus y1 is 70 is equal to m, which is negative 30, times x minus x1 is 1. You could just leave it here because it doesn't tell you what form of line you should put it in, so you could just leave it right here. If you wanted to go ahead and write it in slope-intercept form, you could by distributing the negative 30. You would have negative 30x plus 30, and then adding 70 to both sides. You would get y is equal to negative 30x plus 100. So you can leave it in either form unless your problem asks for a specific form, and then you need to give it in the form asked for. Okay, number 2, we want to look at that one. So if I'm looking at the change in x value, I see each time I am increasing by 1. So I'm adding 1. And now I want to see if I can find a pattern in the y's. So the first thing I look at is if I add 10 here, and then I add 10 again here, that does not work because that's not what's happening. So it means it's not linear. I'm not adding the same thing each time. Now let's look at multiplication or dividing. So 10 times 2 is 20. 20 times 2, is that 40? Well, yes. Is 40 times 2 80? Yes. So since this is a multiplication each time, this would be an example of an exponential function. Okay, to find an exponential function given 2 points, we did that a minute ago. So we have to y equals a times b to the x. So we're going to plug in y, which is 10, is equal to a times b to the x, which is 1. So this is 10 is equal to a times b. I can solve for a by dividing by b. So a is equal to 10 over b. All right? Remember, that's what you want to do with your first point, because then you're going to use that in the second point. So the second point is y is equal to a times b to the x. We have 20 is equal to a times b to the 2. And now I'm going to plug in this a value that I found from the first point into the a here. So that'll be 20 is equal to 10 over b times b squared. And then you can reduce, so b into b squared, we'll just leave a b. So this would be 20 is equal to 10b. Then you can solve for b. Divide by 10, you get b equals 2. Okay, now remember, the next thing you want to do is take that value and plug it back in over here so you can solve for a. So a is equal to 10 divided by b, which is 2. So that means a is 5. So now you're going to use the a value and the b value to write your function. So y equals a, which is 5, times b, which is 2, to the x. And that would be your function.